Now in these cases we have to write down the product of propanol. Propanol is CH3, CH2, CHO. So this molecule is basically CH3. You have CH2, CHO. So this is propanol. And now initially first case is lithium aluminum hydride. So if this is treated with lithium aluminum hydride is LaH. So this is a reducing agent, so it will reduce, so you will have CH3, CH2 and CH2OH. Now the next is sodium borohydride. This is NaBH4. This also do the same thing. So if we have NaBH4, so part B says you have NaBH4. This is also do the reduction, so you will have CH3, CH2OH. Now in this case sodium borohydride is slightly milder. Next is hydrogen in the presence of nickel catalyst. So you have C. This says H2 in the presence of nickel. So H2 in the presence of nickel will also act as a reducing agent. So you will have CH3CH2OH. Now what is D? D you have methyl magnesium iodide. Methyl magnesium iodide. So MeMgI. So methyl magnesium iodide. So you have minus plus. So this is the Grignard reagent. So this is your D part. And this says this is followed by acid. So part B, so basically this is followed by acid. So this is a Grignard reagent reaction. This minus will attack on this carbon. So you will have finally an alcohol CH3CH2. And if you do hydrolysis in the next step, O minus will be converted into CH-COH. Now let us discuss E part. So this says this is treated with sodium acetylide followed by acid. So sodium acetylide is this. So you have sodium acetylide CH, and then you have minus here and Na plus. So this is sodium acetylide followed by H plus. So what you will have? You will have the same thing. Now this time this minus will act as a nucleophile. So initially you have CH3 minus as a nucleophile. Now this acetylide ion will act as a nucleophile. So the same product CH3 CH2 COH, and here you have nucleophile C triple bond CH. Now let us discuss F. So this says you have been phenyl lithium followed by acid. So PHLI. This is again nucleophilic attack. So nucleophilic attack on carbonyl compound, everybody knows. So you will have in this place only thing is you will have pH CH2COH, and in this place you will have a pH group. Now next is, so you have Z part is basically methanol containing HCl. So methanol, so you have to treat with CH3OH and containing HCl. HCl will acting as a catalyst. So if you remember, methanol will act as the acetal formation. Aldehyde ketone goes acetal formation. So initially will form hemiacetal and then you will have acetal. So things are easy. So what you have to do is you have to add 2 OCH3 group on this carbonylic carbon. So this reaction is nothing but, so this is something called acetal formation. So you have acetal formation reaction. Now let us say H. So what is the reagent this time? So this time reagent is ethylene glycol, paratoluene, sulfonic acid and benzene. Ethylene glycol. So ethylene glycol, that is CH2OH, and the rest of the thing is basically acid. H plus paratoluene sulfonyl chloride and H plus HCl. Say, so now this is again a hemiacetal formation, and then further is a acetal formation. Now this is both OH group is coming from the same carbon, so this is intramolecular hemiacetal formation. CH2, you will have CH, and now put 2 OH group from the same carbon, so this O and this O, and then you have 2 carbon also. So let us say CH2 here, and here also you have a CH2 group, and these two are connected. So basically you can write something like in a Vater form, something this kind, CH3 CH2 and then CH, and here you can have O. So sometimes generally this form is more easy to write. So this is the same thing. Now this is an example of intramolecular. So this is intramolecular acetal formation reaction. So this is a intramolecular acetal formation reaction. Are you getting? Now let us discuss next. So that is I. So let us say what is this? Aniline, aniline, PHNH2. This is easy, PHNH2. So if you remember, carbonylic compound PHNH2, what will be the product? If you have some idea, that is CH3CH2, and we have C double bond O and H, and now we have PHNH2, here you have NH2 and pH. So what you will do is, in these cases of a reaction, you remove H2O. So if you will remove H2O, things are easy to write. So you will have CH3, CH2 and C double bond CPH, no, NPH. So this is, you have NPH and then you have hydrogen here. So this is the product, you will have PHNH2. So this is a hydrazone formation. And now next you have hydroxylamine. So this is Z. Z is dimethylamine paratoluene sulfonic acid and benzene. Dimethylamine. So this is, so Z, dimethylamine paratoluene sulfonic acid. So you have dimethylamine paratoluene sulfonic acid. So you have a toluene group. So let me write. So you have dimethylamine so this is dimethylamine paratoluene. So let me check. So this is dimethylamine paratoluene sulfonic. Dimethylamine is one side and the next is paratoluene sulfonic acid. So dimethylamine is this. This is not. So I have to write dimethylamine only. So dimethylamine is this. So this is CH3. So let me write on the top. So dimethylamine is this. CH3 you have and N you have. And then you have here CH3 and this is H. So this is dimethylamine, and rest of the thing paratoluene sulfonic acid is basically acting only as a H plus. So what will happen in this case? So this case, in this is a product is called imine. So previous product is called imine. Now in this case product, what will the product? You see what will happen in this case, CH3CH2 COH. And now in nucleophile, nitrogen will act as a nucleophile. So nitrogen, you have hydrogen, CH3CH3. So this will attack and this goes, and then H plus will take, so you will have OH. So after this I can write CH3CH2 COH, and then you have nitrogen. Nitrogen will basically lose one H plus. So I will have CH3CH3. Now this product can easily lose water in the presence of H plus. You will have H2O plus in the next step. So you form H2O plus, and from here you can lose H plus. So let us say you can write something like this. So you can write this H, and in the next step you lose H plus. So if you follow these steps, what you will have? You will have CH3 double bond CH double bond C, and then you will have NCH3 CH3. Basically this carbon also contains one more hydrogen, and this hydrogen is here. And now this product is called enamine. So this product is, you have a ene group and you have also one amine group. So this is the ene group and this is the amine group. So this product is called enamine. So product in this case is, product is an enamine. So you can remember this one. So this time this amine is secondary in nature. So secondary amine reacts and it gives enamine. So now let us discuss K. So what we have in this case? So K is, you have hydroxylamine and then hydrazine. Next case, hydroxylamine is easy. NH2OH, this is hydroxylamine, is easy. Again you have to remove H2O, so you will have CH3 CH2 C double bond N OH. And this compound will exist in basically cis-trans isomeric form. So you have a cis-trans isomeric form. You can make something like this. So this lone pair you have. So it will exist in cis-trans isomeric form. Are you getting or not? So this will exist as cis-trans. Now next is, you have hydrazine, that is NH2NH2. So hydrazine is simply again loss of water. So we will have final product CH3, CH2, CH, and here you have double bond N and NH2. Are you getting? So this is the final product you will have. Now M. So let us discuss M. What you have in M? Product of part M. L is heated in the presence of triethylene glycol with sodium hydroxide. So this means this product is treated with NaOH. So you have this product, and now this product is treated with NaOH. What you will have? So you will have CH3, CH2, CH, double bond N, NH2. Now if you treat this with OH minus or NaOH in the basic medium, what will be the product? Now this is easy to remember. If you remember this reaction, that is CH3, CH2, CHO, and now if I say NH2, NH2, OH minus, this is a Wolff-Kishner reduction reaction. What will be the product? CHO will be converted into CH2 group. So finally we'll have CH3, CH2, CH3. So in this reaction, basically hydrazone is an intermediate. So this is a hydrazone. So in this reaction, first NH2, NH2 reacts, and this gives you a hydrazone and intermediate. And then this hydrazone reacts with OH minus, then gives you a CH2 group. So this is a hydrazone. Now finally it will be converted into CH3, CH2, CH, and this CH will be converted into CH3. Are you getting or not? So you see in Wolff-Kishner reduction reaction, so this is Wolff-Kishner. So in Wolff-Kishner reaction, semi-hydrazone is an intermediate. So this is an important point. Hydrazone is an intermediate. So you can remember this idea. So hydrazone is an intermediate. Now let us discuss N part. So what is N? N is para-nitrophenyl hydrazine. This is easy to find. Para-nitrophenyl hydrazine. Para-nitrophenyl. So you have this product, and this is treated with para-nitrophenyl hydrazine. So this is NH2, and this is easy to write. Same product is same, CH3, CH2, and you lose one molecule of water. So finally we'll have N, and then you have NH. Here you can write one H. Basically this H2O, this H has gone. So you will have N, and then you have this ring, pH ring. Are you getting? And at para position you have a nitro group. So at para position you will have a nitro group. So this is para-nitrophenyl 2,4. No, this is not a 2,4-DNP test because you have only one nitro group. In 2,4-DNP test you have 2 at 4, 2 position you have nitro group. So this is para-nitrophenyl hydrazine. Next is semi-carvazide. What is semi-carvazide? NH2. So this is semi-carvazide. MnO. So you have, this is NH2CO, NH2. So this is semi-carvazide. No, this is not semi-carvazide basically. So you should have NH2NH, CONH2. So this is NH2NH, CONH2. That was basically written as carvazide. This is same as semi-carvazide. Now in case of semi-carvazide you have this nitrogen and this nitrogen. This nitrogen lone pair is in resonance, so this nitrogen lone pair is more nucleophilic. So finally product will be from this nitrogen side. So CH2 you will have, and then you have CH, double bond N, and NH2, NHCO, NH2. So you have NHCO, NH2. This is important. Now let us say P. So what this question says, P is ethylene, ethylidine, triphenyl phosphorane. So this is PH3P plus. This is a halide formation, Wittig reaction. PH3, PPH3, CHCH3. Are you getting? PPH3. So you have PPH3 in this case. So this reaction is a PPH3, and then you have CCH3, CHCH3. So this side you have plus, and this side you have minus. So what will happen? So this is a Wittig reaction if you remember. So I have to insert this whole thing. So I will have CH3CH2. So this is CH3CH2, and then one more CH, and then I will have a double bond, and I have to have this group CH3. And now this is a Wittig reaction if you remember. This is Wittig reaction. Now let us discuss PQ. So what is Q? So this is, let us discuss Q is sodium cyanide acid. Sodium cyanide and acid. If you remember, this is basically cyanohydrine formation, NaCN, in the presence of acid. Now this is a cyanohydrine formation, so CH2, COHCN, and then you have H plus. So this is cyanohydrine formation. Now next is finally is H2CrO4, that is chromic acid. In the presence of chromic acid, it will be converted into aldehyde, get converted into acid. So aldehyde will finally converted into acid. So you will have CH3CH2 COOH. So this is a chromic acid. And now this is a cyanohydrine formation. Cyanohydrine formation. Cyanohydrine formation is not done in the presence of HCN because this is a weak acid. So in case of weak acid, I cannot have Cn minus high concentration. H2CrO4 is acting as a oxidizing agent. So it oxidizes aldehyde to acid. These are basically reduction reactions. So you have lithium aluminum hydride. So this is lithium aluminum hydride, or you can use NaBH4. Both reagent basically gives H minus. This is a hydride donor. So in these reactions, basically reactions happens through H minus. So the first is S3-phenyl 2-butanone. So let us write 3-phenyl 2-butanone. So at position number 3 you have 3-phenyl, and position number 2 you have butanone, that is hydrogen. This is hydrogen, so this is carbon number 1, 2, 3, 4. So this is the 4 carbon you have. Now if you see clearly, this carbon is a basically chiral carbon. So this chiral carbon, so 3, this carbon is S. So people call it a S. So this configuration is a S configuration. So let us my first task is to write S structure of this compound. So this is CH, PH, this side you have CH3. This carbon is a chiral carbon. So I need to write chiral carbon is a three-dimensional structure. Let us say if I write carbon here and one hydrogen that is going inside, so I have to write S configuration. This means anti-clockwise. I have to write something anti-clockwise. Let us say this is the bond that is going outside. This is the bond that is going in the plane. So now which carbon will have higher priority? So this carbon connected with oxygen, priority number 1. This carbon connected with the carbon, but that carbon is also connected with the carbon, so priority number 2, and this is priority number 3. So I have to have something like this. So I have to add priority number 1 here, 2 here, and then I have to add priority number 3 here. If I follow these steps, so now I can write this carbon is here and hydrogen is going in, and then you have carbon number 1, that is COCH3 group is here. So this is your COCH3 group. And then this side you have, so this is priority number 1. I should have priority number 2 here, that is pH, and priority number 3 here, that is CH3. Now if I do reduction of this, that is if I use LAH, what will happen? So this carbon is basically S. This is a chiral carbon. Now this will be converted into CHOH. So let me write first product and then we'll discuss. So you have H, and here you have pH. This side you have CH3. And this carbon is a chiral carbon. Here you have COH and CH3. Here you have hydrogen. One important point, now this carbon is again chiral. So generated carbon is chiral. So this alcohol that is generated is a chiral. Now if you number these things, so this is 1, this is 2. So this carbon is 1. Initially it was 1. This was 2. This was 3. and we have this is 4, so carbon number 4. So this carbon is 4. So you see initially this carbon number 3 was S configuration, so this is 3 carbon S configuration, but now carbon number 2 can be either R or S both. So for carbon number 2 I have two possibilities. So for carbon 2 it can be either S or R. So either S or R. So this means now I will have configuration is 3S 2R or 3S 2S. So there are two possible products. These two products are basically diastereomers. So these two products are diastereomers. Now let us discuss next. So this is 4-tert-butyl cyclohexanone. So you have 4-tert-butyl cyclohexanone. So this molecule, so you have cyclohexanone and position number 1, 2, 3, 4. So position number 4 you have tert-butyl group. This is this group. This is a big group. So whenever you see tert-butyl, always comes mind into the picture, that is something called a steric hindrance. So there must be something a steric. Now this is treated with lithium aluminum hydride, H minus donor. Now H minus will attack here. Now if you see, it will have OH and then you have hydrogen, and then you have CCS3 and CS3. This carbon also contains one hydrogen. Now we have two possibilities for this one. This hydrogen that has been basically H and OH added here. Now you can have a cis as well as trans both. Are you getting or not? So this is a tert-butoxide group and this side OH group. They can be cis or trans. So let me draw the diagram. So you can have something like this. So this is carbon number 1. So 1 OH and H, and carbon number 3 contains H, and let us say tert-butoxide group I write something like this. So this is tert-butoxide. So TE tert-butoxide. No need to write K. So this is tert-butoxide group. Oh sorry, this is not tert-butoxide, this is tert-butyl. So this group is tert-butyl. So this is tert-butyl. So this is tert-butyl. Are you getting? So I can write tert-butyl something like this. So this is this OH. This is a big group, and on this carbon, this is a big group on this carbon. So I can call this as a trans. You can also have a cis isomer of the same compound, in which these two group are basically same side OH, and this side you have tert-butyl. So tert-butyl and hydrogen. So this is basically cis. Now practically these two products should not be same, but theoretically you can say H minus can attack from this side, H minus can attack from this side. You will have equal amount, but practically in this case, because tert-butyl in this case a steric hindrance, so you have a steric repulsion. In this case a steric repulsion is less, so trans product will be more. So trans product will be more than cis product, more than cis. Now let us discuss next one. And similarly in this case also you will expect that these two diastereomers should be 50-50 ratio theoretically. So this is 50%, another is also 50%, but practically this is not the case. Practically this is not the case. Now let us discuss C part. So this is easy, I have to go fast. C is this, and now again you have to do reduction. So you have to use the same idea of a steric hindrance. Here you have this molecule, and now here you have double bond O, and then you have something like this. Now you see H minus, you can have either this side, so two product is possible. So in this case again, so let us write these two product. So one product is this. So let us say this is, I will have OH this side and hydrogen this side. So this is one product. Another product, hydrogen this side and OH inside. So I will have this. Basically these products are called indo and exo. Are you getting? So these two products you will have in this case. And this side you will have hydrogen, and then you will have OH this side. So this product you will have two products. If you try to see, these two products can't be superimposed. So these two are different products. If you try to just lift this up and put it here, these two products will not superimpose. So these two are different products. So basically these two are different products. Two products are different. and they are called exo and endo. Products are different. So one is called exo, another is called endo. So in one case the OH group is inside, so I can call this as an endo, and in one case OH group is outside, so this is basically exo. Now again, one can expect these two products theoretically is a 50%, this is also 50%, but actually this is not the case, because the attack of H minus from this side is not favorable because of the steric factor. So steric factor of H minus, a steric factor says H minus cannot attack easily from this side. This means this product is the lesser product and this product is the major product, because H minus can attack from this side. So this is minor and this is basically major. Are you getting? Now let us discuss next one. So this says you have this compound, same thing. This side only you have double bond. So this is D. You have the same compound. So let us make something like this. So here you have a double bond. Only difference. Now if you do reduction lithium aluminum hydride, again I think this double bond O is here, not here. So let us remove this one. Now again you will have two possible products. So OH, one OH this side, another time OH this side. So let us say you can write these two products. So one time let us say OH is this side, another time OH is this side. So this is in terms of double bond, OH and double bond both are same side. But if you have another product, in that case double bond and OH are not in the same side. So you can have something like this. So in this case OH is this side and hydrogen is this side. So in this case you can see this double bond and OH are opposite sides. So let us call this the trans in terms of double bond and OH. So this is cis in terms of OH and double bond. Now theoretically again one can expect that the ratio should be 50% and 50%, but this is not actually the case. You see H minus attack from this side is not favorable because of the lone pair of this double bond, because this bond pair of, so this is the pi cloud you have here. So due to pi electron, H minus attack from this side is less. H minus attack from double bond side is less. From double bond side is less. From double bond side is less. So tell me which product should we measure. So if this attack is less, this means attack from this side is more. So this means this product is major product and this product is the minor product. Easy one. So in this following reaction, you have to tell me which will react faster or either which will have higher equilibrium constant. So rate of reaction, one thing, or you have to tell me equilibrium constant. So which will have higher equilibrium constant. So how will proceed? So you see the first part. So you have PHCHO. And now this is PHCHO and the second is PHCOCH3. Now these two compounds, if treated with NaBH4 or LiLH4, this is sodium borohydride. If this compound is treated with NaBH4, let us say this compound is also treated with NaBH4, and then this is the simply reduction reaction. H minus comes, attacks, H minus comes, attacks. Now the rate of this reaction depends upon two kind of factor, a steric factor as well as, so it depends upon a steric factor first and it depends upon electronic factor. These things are discussed in the class. Now in this case, if you see electronic factor, this carbon has less negative charge, less positive charge, because some of the positive charge is stabilized by inductive effect. This will have more positive charge, so attack of H minus on this is more, so rate for this reaction is higher. Are you getting? So let us call rate for this reaction is K1 and rate for this reaction is K2. So basically K1 is greater than K2. Are you getting? So I can say KPHCHO is greater than KPHCOCH3. because of the electronic factor in this case. Even if you take the steric factor, the same thing. In this case, steric crowding is less, but in this case, steric crowding is more. So H minus will attack at this carbon, not effectively, but here it is the case, it will attack effectively. Now B part, so this is equilibrium of hydration, CCl3, CHO, that is also called chloral hydrate we discussed, so CCl3, and then you have CHO. And the next is you have simply CH3CHO. So next is you have CH3CHO. Now if you react this compound with H2O in the presence of acid H+, so you will have hydrate. So let me write this hydrate, COH. Here you have OH. Generally hydrates are not stable, but in this case you have a chloral hydrate H2S plus CH3COH OH H. Now see, this will basically act as a electron withdrawing group. So in this case carbon, this carbon has two positive charges, a lot of positive charge. So it is easy to attack here. Now once this product is formed, this product is a stable, two reasons, because of the hydrogen bonding. So hydrogen chlorine also found hydrogen bonding. So in this case you will have hydrogen bonding. So one favorable factor you have. Another favorable factor you have, attack on this will, attack of H2O basically. In this case is easily because of the more positive charge. So you have more positive charge. But in this case it does not have such kind of factor. So this is less stable. So equilibrium mainly go this side. In this case you will have this side and equilibrium less towards this side. Are you getting? So you can say K equilibrium 1 will be greater than, because mainly this side, so K equilibrium is higher, K equilibrium 1 is greater than K equilibrium 2. Are you getting? So two factor hydrogen bonding, as well as you can think of electron withdrawing group. So attack is easily possible. In this case attack is not easily possible. This will basically give electrons. So this gives electrons. So this sorry, this basically forces H2O out. And now C part you have acetone and 3,3-dimethyl 2-butanone. Acetone, so I have to go fast. So this is acetone, and you have 3,3-dimethyl 2-butanone. 3,3-dimethyl. So 3,3-dimethyl 2-butanone. So this is your 3,3-dimethyl 2-butanone. Now for cyanohydrine formation, let us treat with NaCN, and the next step if you add H+. So this is a cyanohydrine formation. So what you will have? You will have, so only thing is, if you see in these two cases, what is the difference? This side you have CH3 group, but in this case you have CH3C, so a big group, and this side you have a big group. So I can represent these two reactions something like this. Easily I can represent. So CH3C double bond O, I will have R. R means one time this, another time this. This is basically CH3. So let me write so that you cannot have any confusion. So this is CH3. Are you getting? So this is basically CH3. Now you have R, and now if you treat with NaC and H+, you will have cyanohydrine, if you remember. So this is CH3COH. Cn. Cyanohydrine has very crowding this side. Are you getting or not? So if this group is a big group, this will force to go this side. Are you getting? One thing. And so this means a steric factor. So either Cn minus. It is not Cn minus, easy for Cn minus to attack here, but it's not easy to attack here because of this steric reason. So in this case reaction will go in the forward direction, but in this case reaction will come in the backward direction mainly. So I can say in this case K equilibrium is greater than 1. So let us say this is 1 and this is 2. So this is K equilibrium 1 is greater than K equilibrium 2. So K equilibrium 1 is greater than K equilibrium 2 because of the steric factor. So let us say D part. So what you have here? So you have acetone and 3,3-2-methyl 2-butanone. Rate of reduction with the sodium borohydride. Same thing. Now same thing. You see, you have this and this. Now I change R. In this case H minus will attack. So in this case again, it will have bulky groups. So attack for H minus is not easy in this case. So again you will have rate for the first case K1 is greater than K2. when I see rate, basically we have to look for the transition state. When I see equilibrium constant, in that case we have to see the stability of reactant and product. So you see, in these cases even transition state is less stable, because in the transition state H minus is here in this case. In this case H minus will, so you will have less crowding in the transition state in this case. In this case you will have more crowding in the transition state. So you can say for rate generally we look for transition state. So for rate we look for transition state. We look for transition state. In these cases, in this case, basically a transition state is more crowded for bulkier group. Are you getting? So you have a bulkier group, so this is more crowded for a bulkier group. So basically we'll have more crowded, so this means we will have, this is here, and now if you have less crowded, if you have more crowded, this is here. So activation energy is high, so in this case activation energy low, so this is more crowded, this is less crowded, so this is less crowded. So in this case rate is fast, and this case rate is slow. Are you getting? So less crowded, rate is fast. Now let us say E part, what we have. So we have basically CH2O, so that is basically a acetal. So this is hydrolysis of acetal. In one case you have again CH3 group. So let us say CH2, and then you have OCH2CH3, I think. OCH2CH3 two times. So you have OCH2CH3, and then you have OCH2CH3. The next is you will have something like CH3 CH2 CH2C. This time you have, let me see, this is OCH2CH3. So this compound you have C, this side you have CH3, this side you have CH3, but now you have OCH2CH3, OCH2CH3, and now you have to tell me the reaction in the presence of acid. So acid, you will have acid catalyzed mechanism. So let us say only thing is, in this case, one case you have two CH3 group, in another case you have two hydrogen. So if you see what will be the mechanism, you have CH. Let us say in this case, let us say first discuss about CH3 case. You have OCH2CH3. Here also you have OET. What will happen in the first step? This H plus goes here, and then you can remove this one. So you will have CH3 COET. And now stability of carbocation in this case is important. So if we have a secondary or tertiary carbon, this is more stable. So stability of carbocation is easy. So in the next step, you can easily this reaction go can forward. But if we have, so this means in the next step H2O can attack, and then you can have H, you can lose H and this group. So you will finally, so you can do this reaction. Finally you have COCH3. But now see, what is intermediate? Intermediate is a carbocation. So in these two cases, which will have faster? So this will react faster. Even the equilibrium constant for this is higher. So this means if you have these two compound, in this case you will have this product. So let me write product first. In this case, the first case, what will be the product? So you will have HCOH. What will the product in the second case? We have already written CH3 COCH3. Now if I say equilibrium constant for this reaction is K equilibrium 1, and for this reaction equilibrium constant is K equilibrium 2. So I can clearly say K equilibrium 2 is greater than K equilibrium 1 because of the carbocation stability. So K equilibrium 2 is greater than K equilibrium 1. Now this problem is related to dissociation of cyanohydrine. If you have a cyanohydrine, it can dissociate in either aldehyde or ketone corresponding with R dash, and it gives you HCN. Now what are the factors that will basically depend? What are the factors on which this K dissociation will depend? Can you think of? So let us discuss this problem. So we are interested in K dissociation. So this time we are interested in K dissociation. Now you have a cyanohydrine. Cyanohydrine you can have either aldehyde or ketone. So let us say this is the cyanohydrine you have. And this cyanohydrine of aldehyde, it can dissociate, and it can give you aldehyde plus HCl. Are getting? You can have ketone or COH, CN, CH3. Let us take CH3, and this case you have again K dissociation, or C double bond O CH3, and then you will have HCl. Now see, what are the factors that will depend this K dissociation? If you have in this side more strain, that is more steric hindrance. In this case, you have hydrogen, cyanide, CN and R group, OH group. In this case, you have more strain. You have a CH3 group. Are getting or not? So in this case, you have more strain. So in case of ketone, you have more strain, more steric hindrance. So in case of ketone, you can say more steric hindrance, more steric repulsion. So if ketone basically loses HCl molecule, it forms this, and now this molecule has relieved the steric hindrance. Are you getting? And this molecule, so this means it has released more steric hindrance. So this is more stable compared to this. So this means K dissociation for ketone is more than K dissociation of aldehyde due to the steric factor. So now I can say K dissociation for ketone is greater than K dissociation for aldehyde. So this is greater than for aldehyde. Are you getting? Now you see, now I know everything. We can check this same thing here. Now you see, in this case you have, so this is the cyanohydrine of ketone, and this is for aldehyde. So this means this will be K dissociation for this is larger. This is from ketone. So K dissociation for this is larger. So K dissociation for this is larger. Now similarly, you see here, in this case this is coming from aldehyde and this is coming from ketone. Ketone wants to lose easily. So this is, for this molecule, K dissociation is again larger. Are you getting? So K dissociation for this molecule is larger. You can write down the product also after losing the HCN. So easy. In this case, you see, you have R is CH3CH2. So R is CH3CH2. In this case, R is CH3, and also you have one CH3 this side, that let us call R dash. And this is pH, so this is aldehyde, so simply R is pH. This is ketone, so R is pH, and CH3 there itself. Now these are easy reaction. So first one is basically acetal formation. So this is acetal formation reaction. So what you will have? You will have this compound. This side you have OCH3 group, so OMe. Let us call here also I have OMe, and then I also have OMe group here, and there is a Br group. Now this is COH. So what will happen? So this will be CH. Let us put this side you will have O, and this side you will have O. 1, 2, 3 carbon. So you should have 3 carbon. So let us say CH2, CH2, and then I should have one more carbon, something like this. So 1 carbon, 2 carbon, and 3 carbon. So middle this you will have 1, 2, 3 carbon. So this is the intermolecular acetal formation reaction. Are you getting? So you have 1, 2, 3, 4 carbon here, 4 bonds here. Now this reaction, so this reaction is something like hydroxylamine NH2OH. You can remove 2H2 from here. So this is a something related to oxime formation, something related to oxime formation. It's not exactly oxime formation. In case of oxime, this side you have NH2OH, NH2OH. Are you getting? So this side you will have this compound, and now here I have OH, this side I have OME, and this side I will have CH, double bond N, OCH3. Are you getting? So this is the final product. Now in this case again you will have same type kind of thing. You have to remove H2O. So you will have CH3, CH2, C double bond O, and let us, oh, sorry, this double bond O has gone basically. So C double bond N, and then we will have one hydrogen N, and then you will have N contains two CH3 group. So you will have Me this side, another Me this side. So this is the final product you will have in this reaction. This nitrogen contains lone pair. Now this is the reverse of acetal formation, that is dissociation of acetal. So this reaction is nothing but hydrolysis of acetal. So reverse of acetal. So that is hydrolysis of acetal. So if you do this one, so this will be converted into aldehyde. So you have CH3, and then you have a ring, and then CH3, and then here you have CH2, and now this group will be converted into CHO. So that is aldehydic group. Now this is again, what is this? So this is a cyanohydrin formation. So easy one. So what you have to do is you have to add OH and CN. So this is the cyanohydrin formation. So let us say you have PH, COH, and then you will have CN, and then this side you will have CH. So this reaction is nothing but cyanohydrin formation. So this is cyanohydrin formation. Now what about this? This is again something of loss of H2O, but this is a secondary amine. Secondary amine gives methaldehyde or ketone gives enamine, if you remember. So what will happen? First step, this nitrogen will attack. So first step is something like cyanohydrin formation. You will have OH. This side you will have CH3. This side will have nitrogen, and this nitrogen is basically connected by a ring. So this is the final product, but this is not exactly the final product. It will lose H2O in the presence of benzene and heat. So it will lose H2O. So I have to lose H2O only from this side. Hydrogen I have only this side. So I will have PH, and this is COH double bond. So this double bond, if I lose H2, I will have a double bond. So C double bond CH2, and this side I will have nitrogen, and this nitrogen contains oxygen. So this is the ring. So this product is basically called enamine. So this is a enamine formation. So in plus amine, and that's why this is called enamine. Are you getting? So this is secondary amine gives enamine. Secondary amine with containing secondary amine with aldehyde or ketone, it gives enamine. So you can remember. So this is basically secondary amine. Okay, let us discuss this problem. So this is related to writing reactions. Easy one. So we have a compound. This compound is given to you. So there is a 5-membered ring, and there is a double bond O. Now the first step is Wolff-Kishner reduction, NH2 NH2OH minus. This is NH2 NH2OH minus. Wolff-Kishner reduction in the presence of hydrogen and OH minus CO group will be converted into CH2. So the first step is easy. So you have to have this, and then here we will have 5-membered ring. So CO has been converted into CH2. Now the next step is, this compound is compound A. Compound A on treatment with metachloroperbenzoic acid, MCPBA. If you remember, metachloroperbenzoic acid gives epoxide formation. So you will have in the next step one epoxide. So here you have something like this. So you have a 5-membered ring here, but now this side you have a epoxide. So epoxide formation. So this compound is epoxide. Now further question says, this on reduction with lithium aluminum hydride gives C. So this is basically B. Now if you use lithium aluminum hydride, LaH, it will also reduce to epoxide. So what will happen? H minus will come. This will attack from here, and this opens up. So this epoxide will be reduced to alcohol. So you have something like this. So epoxide gets converted into alcohol. So epoxide gets converted into alcohol. So this is epoxide, this is the reduction reaction you have. Now the next step, so next part says oxidation of C with chromic acid gives D. So this is chromic acid H2CrO4, and this is alcohol, secondary alcohol. This will be converted into ketone. So this is converted into ketone. So finally we'll have a ketone. So the final product you have something a ketone. So here you have a ketone. You can count number of carbon. So you have 6 carbon, 7, 8, 9 carbon. How many hydrogen you have? 2, 4, 6, 7, 8 and 10, 12. 12 plus 2, 14. So you will have 14 carbon, 14 hydrogen, and you will have 1 oxygen. You can check the molecular formula. So this question says same thing, C9H14O. Now this question says we have formaldehyde. So formaldehyde is given HCOH and initially contains oxygen 16. Now if this formaldehyde is treated with water and the water contains oxygen 17, labeled oxygen, now you have hydrate OH, OH, and this oxygen 17. So question says hydrate, so this is the hydrate and this is the formaldehyde. Are you getting? So this is formaldehyde. So hydrate as well as formaldehyde both contains oxygen 17. This also contains labeled oxygen 17. How this is happening? So initially you are taking oxygen 16, but now this formaldehyde also contains labeled oxygen, that is oxygen 17. How this is possible? So we have to answer this question. Now this is possible only if equilibrium takes place. So let us say you have formaldehyde, you have oxygen 16 here, and now we know hydrate formation is reversible. So if you have H2O and this oxygen 17, so you will have hydrate, that is here you have OH and OH. So one oxygen is 16 here, one other oxygen is 17 here. Now this I have two possibility. Now in the next step I can lose H2O. So if I lose H2O, so if OH this and hydrogen this, so if I push this, so if I flow the arrow this way and push this OH, I will have CHO. So I will have H CH double bond O 17. Now if I push this hydrogen, this OH, so if I flow this arrow this side and this goes this side, so in this case reaction will go back, so you will have something like this. So this formaldehyde. So you see this explains formaldehyde. Now you will have two kind of formaldehyde. You will have formaldehyde that contains oxygen 17. We will have formaldehyde that contains oxygen 16. You will have a hydrate, that is zemdiol. So this is zemdiol, zeminal diol. So this is a zeminal diol. So now zeminal diol can go either in this direction now or you can go in this direction. Initially you will have more this, but after some time equilibrium mixture, you will have oxygen 17 also, because this bond is slightly stronger. So as time will go, this will have the major and this will be the minor. Are you getting or not? So this will be the minor after some time, and equilibrium mainly will have this compound because of CO17 bond is a stronger. So this bond is a stronger. So this is bond is a stronger, and that's why things are happening something like this. So we have explained why equilibrium mixture contains diol that has oxygen 17, and we also have a formaldehyde that contains oxygen 17. Are you getting? Now this question says if benzaldehyde is treated with 1,2-octane diol, so you have benzaldehyde, that is BHCHO, and if this is treated with octane diol, so you have 8 carbon, 1, 2, 3, 4, 5, 6, 7, 8. Now you have 1, 2 position OH group, so here you have 2 OH group. This is 1,2-octane diol, and if this is treated, this gives a compound of molecular formula C5H22O2. Now this compound is basically a mixture of two compound equal product, so two product. Since these two products have same molecular formula, it looks like these two are basically isomer. So these two are isomers. Now this is done in the presence of acid, para-toluene sulfonic acid. This reaction is done in the presence of acid. You see, there are two oxygen here. It looks like this is the acetal formation reaction. So you have aldehyde and you have 1,2-diol. 1,2-diols are also called vicinal diol. So this is an example of vicinal diol. Now this will give you a acetal. So this reaction looks like acetal formation reaction. So this is a acetal formation reaction. Now let us write the mechanism or the product for this reaction. It is easy to write. You have PH COH, and in this react with C, let us write 2 carbon. This carbon, both carbon contains OH. So this is carbon number 1, this is carbon number 2. Carbon number 2 contains 3 to 5, 6 carbon. So let us write CH2 whole 5 and 1 CH3. Here you have hydrogen. You can always put the hydrogens. Here also you have hydrogen. Now you have this lone pair. So what will happen? You have to remove H2O. So you have to attack here, you have to attack here, and then you have to form acetal. So I can form acetal from this. So let us write acetal formation. Acetal formation happens in the acid medium. So you will have C, and this side you have pH. This side you have hydrogen. Now you will have oxygen. This side also oxygen. This is connected to the carbon, carbon number 2. And this is again connected to the carbon, carbon number 1. Carbon number 1 contains hydrogen, hydrogen. This carbon number 2 contains hydrogen and CH2 5, CH3. Now this means there are a 5-membered ring. You have a 5-membered ring, 2 oxygen. So let me write this product. C, you have PH, H, and then you have 2 oxygen, and then you have carbon. So these are the carbon. Now this oxygen, so let us call this as a carbon number. This carbon, oxygen, and this carbon contains hydrogen. So this carbon just beside the oxygen, you have hydrogen here, and you have one molecule, that is CH2 whole 5 CH3. So this molecule. What about this carbon? This carbon contains only 2 hydrogen. So let us put these 2 hydrogen. Now see, the question says there are 2 possible products, and this is always possible. You see, this carbon contains 2 and this carbon also contains 2 groups, so you can have a cis as well as trans. So this group and this group both are the same side or both are the opposite side, so you will have cis and trans. You can make this diagram. So you have, let us say in one case, pH is inside and hydrogen is upside. In this case, hydrogen is again upside, and this group is inside. So this is hydrogen, and this is CH2 whole 5 CH3. So this group is basically both big groups are downside the plane. So this is cis isomer, and you will have a trans isomer of the same compound. So you will have trans isomer. In this case, hydrogen, let us say, is upside, but now this is CH2. Let us put this is inside, CH2 whole 5 CH3. This is inside, but now I have to change here. Now this time hydrogen is inside and pH is upside. So in this case, big groups pH and CH3 are opposite. So this is basically anti-isomers. Let us say this is a trans. So 2 possible product. You can check the molecular formula. Molecular formula is C15H22O2. C15H22O2. So this is always good idea to check the molecular formula. You have, so 1 plus 5, 6 carbon, 7, 8, 9, and pH group will have 6 carbon, so 15 carbon. You can count hydrogen. 5 hydrogen here you have, and 1, 5 plus 1, 6 plus 2, 8 plus 9 plus 3, 9 plus 3, 12 plus 10, that is 22. There are 2 oxygens. So this molecular formula is okay. So let us say this problem, this says we have cyclic hemiesters are given. So these are cyclic hemiester. If carbon is connected by 2 oxygen and this oxygen is again connected by the carbon, then in that case you have a hemiacetal. but in this case this carbon is connected by one oxygen and one OH, so this is a basically hemiacetal. So this is a hemiacetal. So if you see, this is a hemiacetal. Now this hemiacetal is formed from a carbonyl compound. So we have to write down the open chain structure for the carbonyl compound. So let us say how will you proceed for this. So you see in this case, if you remember, I can remove oxygen. So let us say I have oxygen and hydrogen. So if I try to force this one, so let me write again so that you can understand. You have oxygen, hydrogen. There is oxygen and hydrogen. If I force something like this, so if I remove this bond, make a carbonyl compound, this goes here, and if I attach hydrogen, I will get the corresponding carbonyl compound. So this means I should have, so this oxygen and there will be OH. So let us put OH here, and now there will be double bond O, and there is a hydrogen. So this is the carbonyl compound. Are you getting or not? So this is the carbonyl compound. If I attack this oxygen here, I will get this hemiacetal. So this is the open chain structure. So this is the intramolecular hemiacetal formation. So this is example of intramolecular hemiacetal formation. So this is the intramolecular hemiacetal. Are you getting? Now let us discuss next. So you have this one. You can try yourself. In this case, you have OH bond. So you push this bond this side, this goes this side. So you will get the product. Are you getting or not? So let us write. So you have a this, and this, and there we will have. So I have to remove this one. I will have a double bond O here. So let us put double bond O, and I will have one hydrogen also. Now this oxygen will contain OH group. So there will be OH. And then the same things I have to simply copy. So this will be the product. Now what is happening in this case? Again intramolecular hemiacetal formation. If attacks here, you will get this compound. So this is again intramolecular. So hemiacetal formation, final product is cyclic. So this is the final product is cyclic in nature. This is again hemiacetal. So this is a hemiacetal. So this is hemiacetal. Now let us discuss this one. So next one. So you have this compound. Now this is not hemiacetal. This is basically acetal, because you see this carbon is connected by two oxygen. So it's easy. It's easy. So this means there must be a CO group. And now this oxygen will form OH, and this also will form OH. So this is a basically acetal. This is not a hemiacetal. This is a acetal. And now what you have to do is you have to put a double bond O here. So let us write. So make a frame of 6 members. So you will have this. And now this carbon will contain a OH group. So let us say this carbon contains a OH group. And now this carbon is here. And this contains CH2CH3. So this is ET. CH2CH3 is ET. And now this carbon contains another OH group. Another OH group. You can put this OH group downside if you wish. So this OH group is something like this. So what is happening in this case? This is the intramolecular hemiacetal formation. One time this oxygen is reacting, another time this oxygen is basically attacking. So you will have a acetal. So this is finally acetal. So you have intramolecular acetal formation. Again final product is cyclic because the reaction is intramolecular. Now in this case, you see again this carbon contains two oxygens. This is a acetal. So this is again a acetal. Now what you have to do? You have to do the same thing. You have to put a double bond O here, because I have to remove this two double bond O. So put a double bond O here. It will become OH. It will also become OH. So let us make this diagram. So you have a 6-member ring this side. So you have a 6-member ring this side. Are you getting? Now there is a OH. There is CH2OH. So this is CH2OH simple. And now this you will have OH, because this has been gone. And now there is a double bond O. So at this position you will have, let us say, make slightly a smaller. So I can put this double bond O here. So you will have a double bond O here. Are you getting? Now this carbon is again connected by a ring. So you will have this. And now this oxygen will have OH group. So you will have OH. Now here you have CH2CH3. CH2CH3. So this is the final product. You can write the same thing in an open chain structure. So let us write open chain. You have 1, 2. So let us count 1, 2, 3, 4, 5, 6, 7, 8. you will have 9 carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon. Carbon number 1 contains OH. Carbon number 2 contains CH2OH. So this contains CH2OH. Carbon number 3 contains OH. Carbon number 4 nothing. So this is 1, 2, 3, 4. And 5 contains C double bond O. So this is carbon number 5. 6 nothing, 7 nothing, 8 you have CH2, CH3. So this 8 contains ET group. And what about 9? So 9 contains OH. This is the final open chain structure. Are you getting or not? So you can always put the hydrogen in the middle. So hydrogen you can always form. So this is CH2OH. This is CH. So this is CH. You will have only one hydrogen. CH, CH2OH, and then you have CH2, and then you have C double bond O, and then you have CH2, CH2, and then you have CHET, and this is CH2OH. So easy one. Now this says this double bond is able to capable of showing stereoisomerism. So you can have cis or you can have trans. When this and this are of same priority, so this is cis. When you have lowest priority, two lowest priority groups same side, this is cis. Cis is also in this case called Z, so we will call cis as a Z, and trans, that is basically E. So in case of trans, you have two opposite groups, that is a big groups should be opposite, that is the bigger priority should be opposite. Now this is the lowest priority. Lone pair is taken as the lowest priority. So I have halogen as this lone pair. Among this, nitrogen lone pair is always taken as lowest priority. Are you getting or not? So this is lowest priority. Now let us write down the structure for this compound. So you have CH3CH. So this side you have hydrogen, this side you have CH3, and then you have a double bond nitrogen. And now it's a lone pair. I need Z. This means Z means this is cis. Cis means two lone pairs. So two same priority should be same side. So this lone pair, this is this side, and then you have this side CH3. So this is your Z isomer, because this is the lowest priority. So priority of hydrogen is low, and priority of this lone pair is compared to this CH3 is low. So same priority order, low priority same side. So low priority same side, that is cis, or this is same as Z. Now let us discuss next one. So this is acetaldehyde oxime. So oxime of acetaldehyde. So you have CH3CHO. This is acetaldehyde, and if you remember NH2O, which is called oxime, NH2OH. So if I remove from H2O, I will get acetal oxime. So acetal oxime is this CH3C, and then you have a double bond NOH, and here you have a hydrogen, and here you have a lone pair. Now you have to write E, that is trans. So you have to write trans isomer of this compound. This means two same priority should be not same side this time. So let us say CH3 this side you have, hydrogen this side you have, and now this is the lowest priority group. Now lowest priority group is lone pair this side, they are opposite to each other, and this side you have OH. So this is low priority in this case, and in this case this is the low priority. Basically they are opposite to each other, so this is a E isomer. We cannot call this as a trans. Basically trans and cis is defined only if you have these two groups and these two groups. So carbon contains same group, something like this. So you have cis trans is defined only in this kind of case. You have AB, and here also you have AB kind of atom, then only cis trans is defined. Now let us say 2-butanone hydrazone. So 2-butanone is this 1, 2, 3, 4. So this is 2-butanone, and this reacts with hydrazone. Hydrazone is what? NH2 is hydrazine, and the product is called hydrazone. So if this reacts with NH2, what you will have? You will have one side CH3, another side CH2CH3. So you will have ET group one side, and then you have a double bond N, and then one side you have NH2, and then you have a lone pair. Now you need a Z isomer. Z means cis, so you need cis isomer. So cis isomer, this means C double bond. Now this side you have nitrogen, and lone pair and lowest priority should be same side. So this is the lone pair, and this side CH3 is the lower in priority. So CH3, this side you have ET, and then you have here you have NH2. So this is the same priority. So this and this are low priority, are the same side. So this has a low priority and this also has a low priority. So they are same side. So this is a Z isomer. Now let us discuss next one, acetophenone. So this molecule is called acetophenone, PHCOCH3, and this reacts with semi-carbazone, semi-carbazide. If you remember, we discussed NH2 CO NH2, NH2 CO NH, NH2 CO NH2. So this molecule is called semi-carbazide. So this molecule is called semi-carbazide. So you have to remember this name. So this molecule is called semi-carbazide. Now in this case the product is semi-carbazone. So you have PH, C double bond O. This side you have CH3 and then you have NH2. This nitrogen will attack basically. So you have NH2 and then you have NH and then you have CO NH2. So if you remove hydrogen H2O from here, so if you remove H2O, so what will be the product in this case? So you can write the product. So you will have PH. So let us say you have PH, CCH3, and then you have a double bond N. And one side you have a lone pair, another side you will have NH, CO, NH2. Now I need Z or E. I need E isomer. E means, so E isomer, this means this should be opposite. So this is low priority here. And in this case, this is the low priority. So this should be opposite. So we will have this N lone pair you have here. And then this side you will have CS3. And this side you have PH. And here you have NH, CO, NH2. So this is basically E isomer. Are you getting? Now mechanism for this reaction, this is basically called Baeyer-Villiger oxidation. So we will discuss the mechanism for Baeyer-Villiger oxidation. So this is a oxidation reaction because we are injecting one oxygen. So Baeyer-Villiger oxidation. So we are injecting one oxygen. Sometimes this reaction is also called oxygen insertion. So what is happening? Oxygen atom insertion. So in this case, one oxygen atom has been injected. Now let us say what will happen in this case. If you remember, this is a per acid. So PHCOOH. So this is a per acid. So what will happen in this case? You have cyclopentanone, this molecule, and we have OH, O, C double bond O, PH. Now this will act as acid. So let us assume in the first step this acts as the acid. This takes one H plus, you will have this step. So this is simply protonation. So first step is protonation. You have H plus. Now this oxygen will have a positive charge. Now in the next step you will have O minus here. Now in the next step you can attack this O minus. This will act as a nucleophile. So now in this step this will attack here and this goes here. So if this happens, you can write what will happen in this case. You will have this side you have OH and then you have this O, COPH. Now if you remember, you have some idea what will happen in the next step. If you remember, whenever you have this peroxide bond, so we have to remove. So I have one idea, that is I have to remove this peroxide bond. So remove this peroxide bond. So I have to break the peroxide bond. Break the peroxide bond. This is the idea I have. Now once if I break the peroxide bond, what I can do next? This oxygen will have a positive charge. If you break this bond, something like this, then this oxygen will have positive charge. So I will have idea that if I shift this one, so this kind of migration if I do, then this carbon will have a positive charge. So if this carbon has a positive charge, that can be easily compensated. If I move this lone pair here and this here, so it will lose one H plus. Are you getting or not? So now I can show the flow of arrow. This is easy task. So you have here OH and you have lone pair, and all this happens in only one step. C double bond O, PH. So this bond flows in this direction. Now you have a alkyl migration and then you have something like this. So let us say if you do these steps, what you will have? You will have C double bond. So now you will have 1, 2, 3, 4, 5, 6 membered ring, and one will be contained by oxygen. So you have a 6 membered ring. Carbon number 1 will have C double bond O, and here you have also H, that is a plus charge, and now you have a 6 membered ring. Here you have oxygen. Are you getting or not? Try to visualize. So this one in the next step, and then you have PHCOO minus plus PHCOO minus. Now in the next step you can lose this H plus, and now this H plus will be compensated by here. So you will have, finally I can write in the next step, so you have COOH. So this goes here. Here you have oxygen. So let us insert one oxygen here. For you it will be difficult because you cannot rub this one. And then if you lose this H plus, and this H plus is taken by PHCOO minus. Basically if you wish, you can make a flow of arrow, something like this. So this takes H plus and this goes here. So you will finally have this product. This is called lactone. So you have a cyclic ester, PHCOOH. So this is a lactone. So this is a cyclic ester. Cyclic esters are generally called lactones. So you see, where vinegar oxidation is generally used for lactones preparation. So where vinegar oxidation used to prepare lactones. You can remember these things. Now this question says, it's a good question. Basically you have a compound that is formed. This is a lactone. If you see cyclic ester, so this is basically a lactone. Now the compound is S enantiomer. So this compound has optically active carbon. So this carbon is optically active. But now one enantiomer is formed. So only S enantiomer is formed in this reaction. Now if you remember, we already said sometime enzyme can selectively used and it can only make one kind of enantiomer. And now this reaction is more like to bear vinegar oxidation reaction, oxygen insertion reaction. So in this case you have oxygen insertion reaction. So what should be the compound A? So we have to find compound A. So this is 1, 2, 3, 4. This is 5, 6. So this is a 7 membered ring. So one oxygen inserted, it is a 7 membered ring. If you don't have any oxygen, then you will have a 6 membered ring. So you have initially compound A must contains a 6 membered ring. And now carbon number 4 contains a CH3 group. So this is 1, this is 2, this is 3, this is 4, and carbon number 4 contains CH3 group. Compound A does not have any chiral carbon. This carbon is not chiral, this is not chiral. So this compound is A, and A does not have any chiral carbon. It does not have any chiral carbon. So what is happening in this case? If you treat this compound, now this is something like bare vinegar oxidation. If you treat this compound with, this is oxygen in the presence of enzyme cyclohexanone monooxygenase and some coenzyme. So this is oxygen in the presence of enzyme. So if this reaction is done, I am only getting S enantiomer. So selective. So this reaction is selective. A stereospecific. You can say this reaction is basically a stereospecific, and there is oxygen. So I have to add one oxygen also. So I have to make a 7 membered ring, not 6 membered ring. So I have to make a 6 membered ring, 7 membered ring. So you will have something like this oxygen. So now this is 1, 2, 3, 4, 5, 6, 7 membered ring, and carbon number 4 contains a CH3 group, and CH3 group is coming outside. So let us rub this one. So this is carbon number 4. This contains a CH3 group, and this is coming outside, and you have hydrogen. So this is a stereospecific reaction. So this reaction is basically a stereospecific reaction, because you are getting only one stereoisomer. So this is a stereospecific reaction. The next part says how would the product obtained by the treatment of compound A will change if I do this reaction with peroxyacetic acid, that is bare vinegar oxidation. So now in this case, if I do the same reaction, but this time there is no enzyme. Now if I do this reaction in the presence of peroxyacetic acid, that is CS3 and COOH. So this is your peroxyacetic acid. Again you will inject one oxygen. Final product is same, so you have a oxygen. And now this is a 7-membered ring. You have carbon number 4 will have CS3. This time no enzyme. This is simply Baeyer-Villiger oxidation. Now this time we will have R as well as S both. No stereospecific. So we will have R product. So this is S. And we will also have, in this case, R product. So R as well as both S. So let us put H here, and the downside you have CS3. So in this case you will have enantiomeric mixture. You will get R as well as S both. So this is your enantiomeric mixture. So in this case you will have enantiomeric mixture. Now let us discuss the mechanism of this reaction. Basically OCH3 minus acts as a nucleophile. So you have a nucleophilic attack on epoxide. So this is a epoxide ring. So this is a nucleophilic cleavage of a epoxide ring. So cleavage of epoxide ring by nucleophile. Cleavage of epoxide by nucleophile. So this is the reaction you have. And now asterically this nucleophile will attack on this carbon, not on this carbon. So this is a bigger group. So let us attack this one here. So you have O, and then you have CH2. This side you have C, and then CCS3 whole 3, and then you have Cl. So this is Cl. Now if you have OMe minus, that is OCH3 minus. Now this OCH3 minus, so let us say minus is here. So this minus can attack on this carbon. This opens up. If this happens, we can write what will happen in this case. So it is easy to write. We will have CO minus. Now this carbon contains 3Me, 3-methyl group, and then this also has a Cl group. And now I have CH2. This contains OMe. Now let us see what is the product. Then you can have some hint. You have C double bond O CCH3. C double bond O. I does not have any Cl. So what is? Now things are very easy. So I am forced to do something like this. So this lone pair basically minus charge will repel this Cl. So if this happens, you can write the product in this case. So this CMe, and there are 3Me. So another Me this side. You will have one more Me this side, and then you have C double bond O CH2O Me. So this is the final product you will have. Are you getting? Now next is, so this is the epoxide in the presence of nucleophile. You have the next part. This says you have this compound. If treated with this, again OCH3 minus, you have a nucleophile. Again what can you do? Again you have to attack here, because this is a more nucleophilic, so positive charge is here. So you can attack this one here. That is OCH3 minus can attack on this carbon. So if this happens, I can directly write down the product. So there are 3Me on this carbon. So there are 3Me. So let us write first. And then you have C, Cl, hydrogen. And then you have O minus. And then you have OCH3 and then hydrogen. Are you getting or not? And now what will happen in the next step? That is slightly understand, it's difficult to understand. You see there are two OCH3 group attached here, but right now I have only one OCH3. So what I can do, this suggests me there should be must one more time attack on this carbon. This is possible if I somehow make a epoxide in the meantime. So let us try to make a epoxide in this case. So if you do this one, what you will have C, and there are 3 methyl groups. So this CMe3, and then you have this carbon. Again you have carbon, but this carbon is connected to the oxygen, and there you have a carbon. This carbon has a hydrogen, and this carbon also has a OMe group. This carbon basically has one hydrogen. So by what you have done, you have formed a epoxide. So this is the epoxide generation. This kind of effect is also called neighboring group participation. NGP. So neighboring group participation. You can write. So this is a neighboring group participation. So this is the oxygen. So it's participating. This is intramolecular SN2 reaction. So this is example of intramolecular SN2. So this is example of intramolecular SN2 kind of reaction. Now let us say now I have epoxide. It's easy. So you have CMe3. So let us put this Me. If I put Me, it looks like there are more steric. If I simply write Me3 minus, it does not give me the feeling of so much steric hindrance. You know. So this HCHOMe. Now see, again nucleophile OMe minus can attack on this molecule. I have two options, either it can attack on this carbon or this carbon. Now this side you have too much steric hindrance, so that's why this minus will attack on this carbon. If this happens, this goes here. So you can write down the product. You will have CO minus, and then you have C, and this is 3Me. So you can write CMe3 in condensed form, and then you have hydrogen, and this carbon will have 2Me group. Now in the next step it can take H plus, and then finally we'll have the same product CMe3, and then you have COH, H, CH, OMe, OMe. So this contains neighboring group participation or intramolecular SN2 kind of reaction. You see this is the final product CH3 whole thrice CHOH CHOMe2, the same product. So this is a quite good question. Now this is an easy problem. We have to write down the structure of R-benzaldehyde cyanohydrine. So this is the benzaldehyde, PHCHO is benzaldehyde, and cyanohydrine of benzaldehyde. So if this compound is treated with HCN, it will form cyanohydrine, PHOHCN, and this is hydrogen. So this is benzaldehyde cyanohydrine. So this is, you have benzaldehyde cyanohydrine. Now this compound basically have a chiral carbon atom. So this carbon is chiral. So what are the groups that this carbon has? So apart from hydrogen, you have OH, you have CN, and you have pH. What are the priority order? So the first is the priority of O, oxygen. So this is the priority number 1, and then you have carbon, and then you have nitrogen. So this is priority number 2, and then you have finally phenyl, that is priority number 3. Are you getting or not? Now we have to write down the structure of R isomer. So we have to write down R benzaldehyde cyanohydrine. So this is R. So we have to write down the structure of R isomer. So S is, R is right. This means when the clock goes right. So right means this. So you have to go something like this. So let us say this carbon is here. Put the hydrogen in the back. And now you have one bond that is coming outside. This bond is in the plane of paper. And this bond is also in the plane of paper. So you see, you have to go something like this. This means you have to put the priority number 1 here, 2 here, and then 3 here. Are you getting or not? So this can be possible only if you have hydrogen this side, and this side you have priority number 1, that is OH, and this side let us say you have priority number 2 here. 2 is CN. So this is CN, and here you have pH. Are you getting or not? So this compound you have, you can always make, this is the hydrogen, this compound is OH, and then you have, this is pH, and then you have CN. So this is your R benzaldehyde cyanohydrine. So this compound is R benzaldehyde cyanohydrine. Cyanohydrine. So this is the cyanohydrine of benzaldehyde. Cyanohydrines are generally optically active because this always contains one OH, CN, and H. So this is optically active. Only this is only R isomer. So this is optically active. Now these are the following conversion. So in this case you have to prepare everything from 2 carbon compound acetyl ethanol. So you have to take a precursor as a ethanol, that is CH3 CH2OH. This molecule can be used. So this is ethanol is available to you. Now you have to prepare this compound. So this is basically a acetal. You see CH3CHOCOET. So I can write this as something like this: CH3CH, and then you have CH. This side you have OET group, and this side also you have OET. Are you getting? So this is basically you have a acetal. So this is a acetal. So how will you prepare this acetal? It looks like I can prepare this acetal. So this is target molecule. So this is the target molecule you have. Now this molecule can be prepared if you have CH3CHO, and if you treat with this ETOH, you will get this compound in the presence of acidic medium. Now ETOH I have already. This compound I have. Now how to prepare this compound? This is alcohol and this is aldehyde. So if I do oxidation of alcohol, that is CH3CH2OH, and if I do pyridinium chlorochromate, if I do oxidation with pyridinium chlorochromate, I will have aldehyde CH3CHO. And now I have aldehyde and I have alcohol, so these two can react. So finally I will have CH3CHO, and this react with 2 mole of CH3CH2OH. In the acidic medium, you can take inorganic reagent H plus, medium is acidic. So finally we will have CH3CH, OCH2CH3 this side, you have OCH2CH3 this side. So this is basically an acetal. Now discuss the next one. Now again you have a acetal. So this is again a acetal. So this is again an acetal. How will you prepare this one? So this is your target molecule. Now this is your target molecule. So you can think basically this target molecule can be formed, or you can break this one. So this molecule can be formed if I broke something like this and this bond. So it looks like I can take CH3CHO. So this can be formed using CH3CHO. Plus you will have CH2OH, ethylene glycol, CH2OH. So if you use these two molecules, you will have this acetal. But now this molecule, we have already said you can prepare this molecule by oxidation. So you have CH2OH that is given to you. You have only alcohol is given. If you do oxidation, limited oxidation, pyridinium chlorochromate, you will have CH3CHO. But what about this? How will you prepare this one? It's easy to prepare. You have CH3CH2OH. Now this time do dehydration, H2SO4 heat. So if you do dehydration of alcohol gives alkene. So you have CH2 double bond CH2. And now I need OH at these two positions. I need OH. That is a one well-known reaction. If you treat with cold KMnO4, that is hydroxylation, you will have OH group attached here. So you will have CH2OH, CH2OH. Now things are easy. You can do acetal formation reaction. So you have CH3CHO, and if you treat this compound with ethylene glycol, CH2OH, CH2OH, in the acidic medium, you will have acetal. So you will have CH3COH. This side also, and there is a hydrogen. So this is a again acetal. So you have a acetal. Finally is acetal. Now how will you prepare this one? You see, you have to break from here, So this is the target molecule. So you have this is the target. You can prepare this target using, if you take formaldehyde, HCOH, and if you take ethylene glycol, OH, and ethylene glycol I have already prepared in the previous case. Now let us discuss about this one. So this one, how will you prepare this one? You have to break the bond. You have to have one carbon. But initially you have been given CH3CH2OH. So this is 2 carbon. I have to remove 1 carbon, and this is possible if I do first. Let us do dehydration, H2SO4 heat, and then let us do, so you have alkene. And now if you do reductive ozonolysis, so first step is ozone and the second step is ZnH2O. So if you do reductive ozonolysis, you will have 2 mole of HCHO. Now this molecule we have already prepared in the first part, that is ethylene glycol. Now this molecule can be treated as this. Things are easy here. Now if you treat this molecule with this, finally you will get the same product. In the acidic medium, if you do this one, you will have H, you will have C, you will have H, and now you have oxygen, you have oxygen. So this is again acetal formation reaction. So this is the acetal. Now let us discuss this one. So try this one. So this is the target molecule. You have the target molecule. How will you prepare this one? So if you see, this looks like a nucleophilic attack of C triple bond CHC minus. So you have aldehyde CH3CHO. If you take this aldehyde and if you take this C triple bond CH minus and let us say sodium plus, you have so acetylide ion. In this case further, if you do hydrolysis, you will get this product. Now this we have already prepared. So if you have alcohol, do pyridinium chlorochromate oxidation, but this compound we have not prepared. So this compound can also be prepared from alcohol. You have alcohol CH3CH2OH. Now do dehydration. So first step is H2SO4 heat, and now H2SO4 heat. If you do dehydration simply, there is no need to write 1 because this is the only one step reaction. So if you do dehydration, you will have CH2 double bond CH2. So I have alkene and I want to prepare alkyne. So what I will do? So let us treat with Br2. Now you have CH2Br, CH2Br. And now if you remember, now this compound can be further treated with NaNH2. So if you treat with a strong base NaNH2, now you will have alkyne. Are you getting or not? So you will have CH and double bond CH. So you will have alkyne. Finally we will get the alkyne. This is used in liquid ammonia. Liquid ammonia is a solvent. Now if you treat this compound with, so now you have this and this. So what you can do is, you can make the acetylide ion of this. So let us treat with this any base NH2 minus, and then you treat with this compound, you will get the final product. So let us first make acetylide ion. You have H, C triple bond CH, and now if you treat with NaNH2, so you will have acetylide ion, and you can take one equivalent of this so that you can have only one side. So C triple bond C minus Na plus, and now if you treat this compound with CH3CHO in the first step, CH3CHO we have already prepared CH3CHO, and then you use the hydrolysis, you add H plus, so finally we'll have this side, you will have CH3, and then you have C, and then you have C triple bond CH. So this is the final product you will have. Of course there will be one OH also, so this will attack on alcohol, so you will have one OH. So where you should have OH? So this compound should contain CH3, so there is carbon that is missing. So let us say this will have one OH group and one hydrogen, and there again you have carbon. So this is the final product you will have. Now discuss the next one. Now this is the target molecule. In this case you have, now it looks like this is acting as a nucleophile. So if you see from here, so let us try to bisect this one. You have CH2 and then you have C triple bond CH. So it looks like this is acting as a nucleophile. But if it's acting as a nucleophile, I should have some leaving group here. So there should be leaving group, then only I can do something. But I does not have any leaving group. So what I can do is, I can use one idea. And the idea I can use is, you have to increase 2 carbon. So you have to increase 2 carbon. So you can use ethylene oxide, that is this molecule. If you remember, if you want to increase 2 carbon, we generally use ethylene oxide. Ethylene oxide. So what I will do is, you have this aldehyde we already have. So let us say you have, and this acetylide also we have prepared. Are you getting or not? So let us discuss this part. So what I can do is, I have this ethylene epoxide, and let us say this acetylide we have in the first part, in the previous part we have prepared this acetylide, and now if you treat this with acetylide, what you will have, this attacks here and this opens up, so you will have O minus, and then here you have C triple bond CH, and now if you do hydrolysis, if you add H plus, so you will have this compound OH. Now if you do oxidation of this, so what is this compound? So this compound is, let me write this side, so you have CH2OH, and here you have CH, here you have CH2, and then you have C, this carbon is here, and then you have a triple bond CH. Now if you do pyridinium chlorochromate oxidation, so if you do pyridinium chlorochromate oxidation, you will have CHO, CH2 and C triple bond CH. So this is the final product you will have. Only thing is, how will you prepare ethylene oxide from 2 carbon? So we have already prepared alkene. So if you have CH3CH2OH, we have already prepared alkene. So if you treat with H2SO4 and heat, so in the first step you do H2SO4 heat, you will have alkene. And now if you do epoxidation, that is acetic paracetic acid RCO3H, that is oxygen insertion reaction, so you will have first alkene and then you can add one epoxide. So this is the final product. So we have already prepared this epoxide. You can use this epoxide here. Now let us discuss this one. So try to use some bisection or dissection. So this is the target molecule and you have to use only 2 carbon. You see how many carbon you have, 2 plus 2, 4. So it looks like you can attack 2 carbon on something 2 carbon. So try to do this one. Easy. So what we can do is we can use some, in this case it looks like this target molecule can be prepared. If I bisect 2 by 2, so I will have CH3 COH, and then if I have something like 2, that is CH3 CH2 minus and Mg plus. So if you have MgBr, let us write, if you have something like this, you will get the final product. Are you getting or not? So what we will have, how will you prepare this Grignard reagent from 2 carbon? This already we have prepared using oxidation. Grignard reagent is easy to prepare. You have alcohol CH3CH2OH. First you treat with PBr3 or PCl3 or SOCl2, you will have CH3CH2Cl, and now treat with magnesium, you will have Grignard reagent CH3CH2 MgCl. And once you have Grignard reagent, this Grignard reagent can be attacked on aldehyde. So you have aldehyde CH3CHO, and now add this Grignard reagent CH3CH2 MgCl, and then do hydrolysis in the next step. So you will have finally CH3 COH. You see, this is a secondary alcohol. Secondary alcohol can be prepared by Grignard reagent synthesis. So this alcohol is a secondary alcohol, and of course this is a chiral also. So this carbon is a chiral. So you have CH3, this carbon is chiral, CH3 CH2. What I have to prepare? I does not have to prepare this molecule. I have done something wrong. I have to prepare only primary alcohol. This is not a secondary alcohol. So this means I cannot use something like this. I have to use something different. So what I can do is, if I treat this Grignard reagent, so this is a different molecule. If I treat this Grignard reagent with ethylene oxide, so that is CH3CH2 MgBr, and if I treat with this ethylene oxide, this molecule, you will have the final product. In this case, you will have this attacks here, this goes here, so you will have a, and do hydrolysis. The next step, you will have CH3CH2 CH2CH2O minus, and this minus you can do H plus, so you will have finally CH3CH2 CH2CH2OH. So important point, you have a primary alcohol that can be only prepared using the ethylene alcohol. You have aldehyde or ketone, you will get the secondary alcohol. So primary alcohol, either you need formaldehyde or you need basically ethylene oxide. So primary alcohol, you need ethylene oxide. You need ethylene oxide. And we have already prepared ethylene oxide. Did you remember or not in the last part? Ethylene oxide. Now this is a conversion. So this is an easy problem. So we have to convert. So this is a conversion kind of thing. Now see, you have to prepare, this is benzophenone PHCOPH. So you have to prepare benzophenone. Finally you need benzophenone PHCOPH. First is benzoyl chloride and benzene. So how will you prepare using benzoyl chloride, that is PHCOCl, and this you have this side bromobenzene. No, this side you have benzene. So if you treat these two compound, How will you prepare this one? This is a basically Friedel-Crafts acylation reaction. If you use AlCl3, this will attack here, opens up, and you can remove this one. If you remember, if you can prepare a electrophile, so no need to explain all this thing. PHCO, pH. So this is Friedel-Crafts acylation. Now let us discuss B part. This says benzyl alcohol and bromobenzene. So I have benzyl alcohol, that is PHCH2OH. This is benzyl alcohol plus bromobenzene. So you have bromobenzene, PHBr, that is bromobenzene. Now what can you do? You can make Grignard reagent of this. How will you use these ideas to prepare PHCOPH? How will you use? Now prepare Grignard reagent of this and do aldehyde of this. So let us do oxidation. So PHCH2OH, if I use pyridinium chlorochromate, this is a, then you will have PHCHO, this is a aldehyde, and now this is PHMgBr. You can always prepare using Grignard reagent using Mg. So if you treat this with magnesium, you will have now PHMgBr, PHMgBr. Now these two reagents, if you react, so if you react PHCHO, that is PHCHO and plus PHMgBr. So if you treat with PHMgBr, what you will have, this minus will attack and open up. So you will have PHCO minus and then hydrogen, and there you will have pH. Now if you do hydrolysis of this compound, so add H plus, finally we'll have PHCOH, pH and H. If you do oxidation of this, you can use KMnO4 here. So if you do oxidation, it will have a ketone, so that is PHCOPH. So this is the final product you have to prepare, PHCOPH, that is the thing. Now next is bromodiphenyl methane. So you have a bromodiphenyl methane. This means methane contains now two phenyl group and it contains one bromo group. And using this, so this contains one bromo. Using this we have to prepare PHC double bond O pH. Things are easy this time. What I can do? I can replace this bromine with OH and then oxidation. So replace this bromine with OH. Many ways you can do. So even if you treat with aqueous NaOH, or you can use PCl5. No, not PCl5. Aqueous NaOH, that will be enough. You treat with aqueous NaOH pH. In this case, reaction will be basically SN1 kind of reaction. Aqueous NaOH or aqueous KOH, you will have PHCH. Here you have OH, here you have pH. Now you do oxidation. So if you do oxidation, that is treat with KMnO4. If you do this, you will have PHC double bond O pH. Now let us discuss the next one. So next you have D part. This is dimethoxydiphenyl methane. So you have two OCH3 groups. So D is this. You have C, this contains a pH, this contains a pH, and now OM is here. OM is here. How will you prepare this compound using this compound? Now if you see clearly, this is a basically acetal. So this is the acetal. Now this side you have a carbonyl compound, this side you have acetal. So this is acetal are always reversible. So if you hydrolyze this compound, hydrolyze this compound, let us take H plus and the excess H2O. In the first step still you can write H plus and excess H2O. H plus and H2O. Now H2O is taken in excess, so I will have this side. If you remember this reaction, now you have PHCHO and H plus. If I treat with H plus and H2O, H plus CH3OH, it will have this compound PHCOH, OMe and OMe. Now this is a basically reversible reaction. If I add excess H2O, reaction goes in the backward direction, Le-Chatelier principle. This means I have to use excess H2O so that I will have ketone. Now let us discuss the last one. You have something like this 1122 tetraphenylethene. So you have tetraphenylethene. So you have this side. This time you have tetraphenylethene. So this side pH, this side pH. this side pH, this side pH, and it's easy this time. You have to prepare PHC double bond OPH, and this is easy. If you break this bond from here, so you will get the same compound. So then you do the reductive ozonolysis. So you can do reductive ozonolysis O3, and the second is ZnH2O. So if you do reductive ozonolysis, this bond will break and final product will be a carbonyl compound. That is, as this is benzophenone. So this compound is called, let me check. This is called benzophenone. So this compound is called benzophenone. So you can remember the name. This is benzophenone. This compound is called acetophenone. PHCOCH3 is called acetophenone. So this is acetophenone. And this is benzophenone this time. Now this time we have to prepare a long molecule. So how will you proceed? So let us say you have the molecule is a CH3 CH2 whole 8, and this is CH double bond CH CH2 CH double bond CH CH2 CH, and then you have a double bond CH CH double bond CH2. So we have to prepare this molecule, and this can be prepared using first is 3,6-hexane deca hexadecan dienol 1-ol. So you see this is a hexadecan. Hexadeca means this is 16. So you have 16 carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 carbon. And now at 3 and 6 position you have an ene group. So 3 and 6. So let us write 1, 2, 3. So you have a 1 double bond here. 4, 5, 6. At 6 position again you have a double bond. Now you have a 1-ol. So at position number 1, let us say you have a ol group. So at position number 1 you have ol group. And now you have a allyl alcohol, that is CH2. Allyl group is CH2 double bond CH2, and then you have CH2. This group is called allyl group. So this group is called allyl group. So we have already discussed. So this is allyl alcohol. Are you getting or not? So this compound we have to let us count the carbon: 3, 1, 9, 10, 11, 12, 13, 14, 15, 16. So this means I have to break from here. So I have to have this molecule plus this molecule. Let us check the position of double bond. So if you see from this side, if I place this OH this side, so same thing, I can write this double bond from this side also. So you see where the position of double bond. So you have 8 plus 1, 9 plus 10. So first double bond is here. So position number 10. This is same thing. So if you count from this side, this is the 10th number position. And then you have 11, 12, 13 number position. So this is 10th. Then you have 11, 12, 13 number position. Are you getting? So double bond is same. So if you write from this side, you have the same compound: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let us write this is 1, 2, 3, 4, 5, 6. Carbon at 3 double bond you have. So carbon 3, 4, and carbon 6, 7 you have double bond. So this is 6, 7. So this is the original compound. Now you have to add simply this double bond. Now idea will be good if I convert this COOH to double bond O, and then I can prepare a halide of this compound. So I am interested in something of Wittig reaction. If you see, Wittig reaction is used to generate C double bond. So let us try something called Wittig reaction. So if I apply Wittig reaction idea, what you have, this side you have CH3, and then you have 1, 2, 3, 4, 5, 6, 7, 8 carbon, that is CH2 whole 8, and then you have 1 carbon carbon double bond. So you have carbon carbon double bond, and there is a hydrogen, of course, there is also hydrogen, and then you have CH2, and then you have carbon carbon double bond, CH, H is there, and then you have CH2 CH2OH. So if I do oxidation of this compound, if I do KMnO4 oxidation, or you treat with pyridinium chlorochromate, because I need primary alcohol up to aldehyde only, so let us treat with pyridinium chlorochromate. So finally we will have CHO. So this is the compound you will have. Now let us say one is ready. Now allyl alcohol, convert this into allyde, that is CH2 double bond CH2 CH2OH. First treat this with PBr5. So if we treat with PBr3 or PBr5, we will have alcohol CH2 double bond CH2 CH2 Br. Now if you treat with PPS3, that is the alide formation. So if you treat with PPS3, this compound, now I will have a alide if you remember. So this is CH2 double bond CH2, and then you have CH2. You will have phosphorus PS3 Br, and this is minus, this phosphorus contains plus. So this is the alide. Now I have alide. So this is alide or ylide, whatever it's called. You have ylide, you have this carbonyl compound, so you can add these two reactions. So you have, let us write, so you have CH3, the top one let us write first. So you have CH3 CH2 whole 8, and then you have CH double bond CH, and then you have CH2, and then you have CH double bond CH, then you have CH2, and then you have CHO. Now this, if this compound is treated with this, now let us write alide this side, CH2 minus PPS3 Br. So this has a plus, so phosphorus has a plus charge. Mechanism we have already discussed. Now this is CH2 double bond CH2. So what will happen in this case? A double bond will be generated. So this is a alide reaction. So in this case, final product will be, you will have the same compound, that is desired CH2 whole 8 CH double bond CH, CH2 CH double bond CH, CH2, and there is a double bond now created, C double bond C. You will have hydrogen also here, and then you have CH2 double bond CH2. So this is the target molecule you have required.